So I'm going to talk about the terradynamics of dynamic multi-legged locomotion in complex terrain. Robots have been envisioned to become a major part of society, and we have already had a lot of robots shown here, terrestrial ones that have already ventured outside the laboratory. Some of them are becoming really good at moving through the real world. Some of the most well-known examples are robotic vacuums, Mars rovers, and self-driving cars. And the approach of robots in terms of moving in complex environment is very often by navigating the environment using geometric maps created by its cameras or other vision sensors. And then what they do is they can transition between different driving modes to avoid sparse obstacles, treating anything other than the flat ground, in this case, as obstacles. And in order for this approach to work well, the premise is that the locomotor-environment interaction has to be well understood, such that the vehicle or robot here can readily be readily controlled to follow the planned trajectory. And we can do this because for wheeled vehicles on paved roads, we have vehicle and tire dynamics, as well as the Terramechanics for off-road vehicles moving in deformable ground. Analogous to this, for flying and swimming, we also have these entire fields of aero and hydrodynamics with many well-established experimental tools, as well as different kinds of models that allow us to not only understand how animals move, but also create devices that move robustly through the complex interaction with the fluid environment. And similarly, for terrestrial non-wheeled locomotion, we also have decades of studies that have revealed the principles of near steady state single mode locomotion on flat rigid ground, which has resulted in beautiful robots that move well on such relatively simple surfaces. And is in fact, because of such fundamental understanding of the mechanics and dynamics of interaction with rigid ground, that have really paved the road for really successful robots that we see today from places like Boston Dynamics. Mark Rayburn was in fact a professor really pioneering the studies of such interaction using relatively simple legged devices back in the 80s and 90s, when he was early in his career, that really have provided the foundation upon which they can add sensing, control, and planning at the high level for these robots to move so successfully. However, when we go beyond such relatively simple flat rigid ground and encounter more real-world terrain, such as desert sand or Martian soil that can deform under the intrusion of a leg, or complex 3D terrain such as forest floor or earthquake rubble, where we have a diversity of large obstacles piled together, these kind of complex 3D terrain, we do not have a good understanding of such interaction with a complex terrain. So in other words, to begin to make progress, we need to begin to create a new field of terradynamics on the same level of aero and hydrodynamics. And I started doing this when I was still a PhD student with Dan Goldman at Georgia Tech. And as you all know, Dan's lab focused on, early in his lab, focused on all kinds of animal and bio-inspired locomotion in granular environment. And I specifically focused on legged locomotion. And so I studied how animals and legged robots move on granular media controlled, much like a wind tunnel controlling fluid, and eventually created granular resistive force theory, which is essentially mapping out experimentally lift and drag forces, which can allow us to predict very accurately locomotion of legged robots. Just a little bit more in depth of the primary conceptual advancement here. So before we started, there already was this huge field of terramechanics, as I had already mentioned, which existed for several decades, and they deal with very large wheeled and tracked vehicles interacting with the formable ground. And one primary approximation that's used for these terramechanical models is that, as you can see from the pictures, the interface of these vehicles with the ground is very often quite flat because the wheels or tracks do not sink in very much. So you can actually use what's called the horizontal plate approximation to measure how stresses depends on depth. For example, pressing a plate in, penetrometer test to measure the pressure as a function of depth. You can also do what's called the beavimeter to characterize the shear forces, shear stresses as well. And then you can integrate these stresses, basically dividing this interface into little horizontal elements, and then sum up the forces, for example, the lift from pressure integrated, or the vertical stress integrated, and you can balance that with the vehicle weight, both statically and dynamically, to then predict the sinkage and the drawbar pull, which is the horizontal net force that it can generate. But one primary limitation of this approach, as actually pointed out by Dr. Becker, the pioneer of this field a few decades ago already, is that when you have a sinkage that is substantial relative to the size of the wheels, then it's not going to work well because you can no longer apply this approximation. And in this case, this is going to overpredict the lift and underpredict the sinkage. And this has catastrophic consequences, such as the Mars rover, as we all know, which got permanently stuck on the surface of Mars. And obviously, we do not then expect this to work for legs. So through robot and animal observations, what we found is that their leg or feet interact with granular media in a very complex way, but you can extract 3 parameters which are relevant here. If you divide up a foot or leg into little segments, you can see that each segment moves at different depth with different orientation and in different directions. We found that the force is insensitive to speed when the speed is low for these small robots or animals. So what we then hypothesize is that if we can use a plate element to measure the lift and the drag force or stress as a function of these 3 parameters, and perhaps we can just simply integrate them over a leg or foot moving along some complex trajectory to obtain the total force, which then allows us to calculate or predict the movement. And this might sound trivial, but in fact it's not in such complex media. We don't know if such integration works. But anyway, here for granular media, we don't have fundamental equations, so we have to measure these forces empirically. But anyway, we did this, and what is really surprising is that when we used different kinds of granular media with many differences in particle properties, we find that the lift and drag coefficient, I'm showing just the lift here for simplicity, turn out to depend on these 3 parameters very similarly. They're proportional to depth, which is not shown here, but what's shown here is the lift coefficient, which is the lift divided by depth, that slope. And you can see that it varies with the orientation and the direction in very similar ways. The only difference is that it's scaled up and down for these different media. And then with this integration can predict, as we can see here, the dash versus the measured experimental data can predict the lift and drag forces quite accurately, which leads to a really accurate prediction of the locomotion of the robot. And this surprising generality leads us to the further benefit that because you have such a general profile, you can still simply press a plate downward to characterize the largest stress here, and then infer everywhere else because it's just a scale. So in other words, this turns out to be compatible with Terramechanics, our first Terradynamics. And because this is based on integration, there should be no reason that it wouldn't work on a small wheel. And in fact, after I had left Dan's lab, I continued to collaborate with people at MIT to test this. And indeed, they found that the predicted sinkage here, for example, from resistive force theory matches the experimentally measured for this very small wheel really accurately, whereas the Terramechanics, as I said, greatly underpredict the sinkage and overpredict the performance. But there is one thing that had really bothered me for several years after I have left, which is when I tried to apply this resistive force theory on the animals. Here, what I did is, this is unpublished data actually, when I plugged the measured kinematics of the animal into this model, basically integrating forces over the observed kinematics, what I found is that the overall vertical impulse that the animal can generate using this resistive force is only can only provide half of what's needed to support its body weight. So what's missing here? And one thing that I speculated is that these animals can actually impact the surface at pretty high speeds initially, and even during the penetration, the foot speed can be somewhat higher for sure than the robot. So perhaps there will be additional forces that's not captured by this quasi-static resistive force theory. So I left with this question, and later, Dan's student, Jeff, had actually performed a very nice study of robot jumping on sand with high impact speed, in which he found that there's what's called the added mass effect. And this has also later been demonstrated using a continuum model developed by Ken Kammerer's group in collaboration with Dan. And this actually is another kind of another thing that has come out of all this resistive force theory is that Ken's group with Dan, Ken's group had actually applied a frictional plasticity theory to actually be able to predict all of these lift and drag coefficients, how they depend on these parameters. And their continuum model further allowed them to more recently add inertial term to capture the rapid intrusion, the foot impact that the jumping robot showed is an impact, like an initial collision, and this is the rapid intrusion afterwards. So in that phase, there's also a large, substantial inertial force that's being added. Yeah, so these both of these kind of added mass and inertial terms can likely explain the missing forces that I had on the lizard. And more recently, other groups, here's Northwestern's work led by Paul Umbenhauer and Kevin Lynch's group. They had actually applied the resistive force theory to perform optimal control and leg trajectory planning for like a robot using this very nice kind of hardware system. They're trying to demonstrate that. Anyway, so that's a brief, a very brief, and I'm probably missing much of the recent work here of the Terradynamics on granular media. So next I will talk about expanding Terradynamics into complex 3D terrain. And this is something I started thinking about after I left Dan's lab and began working with Bob Foe at UC Berkeley. So the motivation here is that we can see that animals, they can really make a diversity of locomotor transitions between many different modes when they move through such complex terrain, whereas robots are still not good at doing so. And when we look at the conceptual knowledge gap, what we saw is that the majority of our understanding of leg locomotion, both in animals and robots, really rigorous dynamical systems theories, has been very relatively limited to understanding how to generate and how to stabilize yourself around a steady state limit cycle-like behavior. Whereas for these kinds of terrain, which actually have been shown by very early studies here that it's obviously not the case. You get constantly perturbed away from your steady state limit cycle behavior. And we still have a relative lack of conceptual framework or even concepts to think about such locomotor transitions. So when I first began working with Bob, what I decided to look at is these little discoid cockroaches, which are native to the tropical rainforests, not only because Bob's lab has them, but also they are just very good at doing moving through such terrain. That's their natural habitat. But you can see a forest floor just seems formidable. You have so many different kinds of obstacles. How do you begin to make progress? Obviously, you don't have homogeneous media such as in the fluids. So the first step I took then was to focus on dense vegetation, which itself is pretty complex and diverse. So what I decided to do is to focus on grass, a representative of dense vegetation, and created these kind of artificial grass, which like wind tunnel, I can then use basically these laser cut paper to generate repeatable experimental setup for repeatable experiments. So through the study, what I found is that the animals actually use many different locomotor modes and transition across them. And each trial might look very stochastic, but when you have a lot of trials over here, almost 300 trials, the animals can actually seem to have some preferred modes probabilistically. So what we have been doing in my lab, a pretty large part of my lab's work has been to expand this into more diverse, kind of distinct kinds of large obstacles. And our hope is that if we can understand how different locomotor modes emerge and how to control yourself to make transitions between them, we can perhaps better understand how animals generate such multimodal transitions and be able to even control or plan robots to do so. Yes, so towards this end, my lab has created a variety of experimental systems, such as these controlled variable obstacles, imaging and 3D reconstruction techniques. This turned out to be fairly difficult to do, to track the animal reliably when you have lots of obstacles. And then we also have this, what we call a terrain treadmill, which allows us to keep the animal on top, moving through many obstacles. Using these variety of tools, we performed a lot of empirical observations of both animals as well as robots going through these kinds of distinct model terrain, and also including the self-riding here, because they get flipped over pretty frequently in the face of large obstacles. And finally, we can then come up with a variety of different kinds of models, ranging from very simple ones to more elaborate ones here. So I won't be able to talk about all of this. I will really highlight one project in which we had made the significant progress to give you an idea of how we integrate these diversity of approaches to make progress. This is led by my PhD student who recently graduated, Ratan. What he is focusing on here is to look at this transition from what we call a pitch to a roll mode. And this pitch mode is really the animal just pushing down the beams, which happens most frequently when the beams are less stiff. And then when an animal is in face of more stiff beams, they very often try to push forward, but quickly transition to this rolling mode through the gaps. So what we can do is to think about the simplest physics model, which actually completely ignores the dynamics and only considers the potential energy of the system. We treat the animal as a rigid body, these legs as these beams as a kind of place with torsional springs at the base. And then when the body is moving in the close neighborhood of these beams, the total potential energy of the system is going to depend on the position and orientation of this body in 3D. So what's shown here is just the cross-section of potential energy landscape. As I said, it's a function of 3D position and orientation, and what's shown here is just a cross-section over the body pitch and the body roll degrees of freedom. What you can see here is that when the body is very close, you have these three local minima basins. In the middle here, you have a pitch basin with 0 roll and a finite pitch corresponding to this state of the system if it falls to that minimum. And if you fall to these two other minima, you would actually roll to the left or to the right. So what looks like might be happening when the animal makes a transition from a pitch to a roll mode, because of the reminiscence of these states to the body poses, is that they are perhaps transitioning hopping out of this pitch basin to which it's initially attracted and reach this roll basin. And to do this, you then have to overcome a potential energy barrier. So is this true that a locomotor transition can be viewed as a barrier crossing transition in which you have to destabilize yourself purposely, on purpose from the attraction to this basin of one mode to reach another? So one very simple naive hypothesis we had is when you look at these animals from my earliest study, they actually oscillate their body quite a bit, which gives them quite a bit of kinetic energy. So if your potential energy barrier is smaller than the kinetic energy, then maybe that shaking itself is going to allow you to make this transition. And this can be particularly useful if you don't have any ability to use sensor feedback. Obviously, animal does have that ability. But to test this simple physics hypothesis, what Ratan did in collaboration with a master student is to make this robo-physical model, which is basically a physical realization of our system. You can drive the system forward and then oscillate it up and down to give it some kinetic energy that's controlled and variable. And then this body can pitch and roll in response to its interaction because of a gyroscope mechanism. Yeah, so here are representative trials where you can see that without body oscillation, it's indeed trapped in that pitch mode when it's right in front in the very middle of the two beams, and just push down the beams to traverse. Whereas when you have sufficient kinetic energy fluctuation, you actually quickly transition from the pitch to the roll mode to traverse. And these are just two trials. We have actually dozens of trials, which we can visualize by tracking the system and plotting the trajectory on the landscape, which evolves as you move forward. And you can clearly see that the trials in which it was stuck to the pitch mode actually all got attracted to this pitch basin, whereas the ones that made the transition escaped from that basin to reach this lower basin, roll basin. So we can use our model and the measured trajectory to actually quantify the potential energy barrier and compare that with the measured kinetic energy. Again, as I said, as you move forward, this potential energy barrier is going to change because the landscape evolves. So you can see that the kinetic energy is greater than the potential energy barrier over here. And that's in fact exactly where we see this transition happens, the mean and the standard deviation. So this confirmed our physics hypotheses in a feed-forward simple robot. And in fact, Ratan had done this for his animals as well. And we found that everything is qualitatively similar, except that for the animal, when this transition happens, the potential energy barrier has not actually reduced to below the kinetic energy level. Yet they can still make that transition. So this means that they have to be doing something active. And a recent study led by my student Yaqing is to had actually quantified in much more detail the body and leg kinematics of even the head, abdomen kinematics of the animal. We found that the animal would spread its legs out when it pitches up, but then reduce the leg spread to likely reduce the roll stability to roll into the gap. It extends one leg and retracts another, likely to generate a roll torque. Further, it actually flexes its head and abdomen quite frequently during this kind of pitching up phase and rolling into the gap and eventually maneuvering through the gap. We don't know what these are doing, and we hypothesize that they're likely to sense this interaction and reduce the interlocking friction when you're moving through this narrow gap. So to further understand how to sense and use such physical interaction intelligently to help you better make transitions, what Yaqing has recently done is he developed a next generation of our robot, which has several 3D force sensors embedded. as well as contact sensors on the surface. Just a quick demo here. As Yaqing touched these kind of front part, you can see these will light up, and we also measured 3D forces. Yeah, so that's just a kind of quick example of what we have done for these cluttered beam traversal. And as I said, we have already done this for a large variety of scenarios, different kinds of types of obstacles, as well as self-righting. And what, again, turned out to be really surprising is that there are general principles. For example, we found that for each one of these, there are not that many modes that the animals or robots demonstrate. It's typically just two to three. And when we use our potential energy landscape approach to look at the landscape, you can see that it is because you have these relatively few and deep basins of attraction to which the system can get attracted towards, and the transitions is then that emerges as the system is able to hop between barriers to make transitions to different basins. We have also empirically, in our experiments, discovered a large variety of strategies that can be used to facilitate such transition that are desired, but also to suppress undesired transitions. And these have advanced the performance of our robots by a really large kind of margin. And conceptually, what we eventually realize is that in order to transition on the landscape, not only can you just passively explore the landscape with kind of noise, like was shown earlier, fluctuations of the kinetic energy, you can also actively steer yourself on the landscape. You can also modify your body shape, basically through actuation, to change the landscape barrier. And you can finally modify your body design, morphology, to add or even remove landscape basins. If you're interested, we have a recent review paper discussing all this. So our hope is that we still are not quite there yet, but we're hoping to further study these active kind of intelligence aspects of locomotion, and eventually we're going to be able to use this framework to predict how to make use of sensory information to sense, control, plan, and learn to make transitions robustly and efficiently on such landscape, making use of interaction with clutter obstacles. And this will complement the well-established approach to allow robots to go to more places. And just last little bit, Fei, my previous lab mate, she's now at USC, and her lab has, herself, when she was a student and as a postdoc, had also done quite a bit of nice work on observing and modeling the leg-large obstacle interaction, shown here. And her group is going to have a couple of talks on that in this session. So finally, I just want to make a few kind of, I guess, observations over the year. Mention a few observations and suggestions that I had over the years that I think is really going to facilitate further progress in this new field of terradynamics. We want to really try to study the organisms in realistic environment, and it is very hard, but it is doable, and we need lab test beds as well as miniature sensors to make more systematic measurements of as many things as we can. And we also want to study more diverse and ideally high-performing organisms for such complex terrain. And all of these is going to also benefit from being able to study free-moving organisms, not tethered, and really try to do it in 3 dimensions, not 2 dimensions. And the robot physical models here can be a very powerful approach, as already demonstrated by some of my early work shown here. It can complement biological studies because it enact and not model the laws of physics, unlike theoretical models that which may get the physics wrong. And also, it is more amenable than theoretical modeling. It can be intractable which can be intractable for complex locomotor-terrain interaction. It can generate relevant locomotor behavior using minimalistic design actuation and sensing, which can be easier to analyze and model. It's also more amenable than the animals in terms of controlling the parameters to test hypotheses in a systematic way, and also vary parameters to discover principles beyond what can be observed in organisms. Finally, it can also be studied open loop first, as we have shown, to isolate the effects of passive mechanics from that of active sensory feedback. And there have been actually a large number of review papers, as well as a book listed here, which had discussed the usefulness of physical modeling and robo-physical modeling. And finally, obviously, we definitely need more interdisciplinary training and integrative teamwork. So my vision for Terradynamics is that eventually, with continued progress, we'll eventually reach the same level of these geometric maps for self-driving, to have these databases of the environmental physics, as well as the actions that you need to make in order to move better, exist in the cloud, coexist, I guess, with the geometric maps to enable robots to do many things in the real world. With that, I'd like to thank my advisors, especially Dan Goldman, also Bob and Ron Fearing, who had really guided me and supported me over the many years, last dozen years, and also my fantastic PhD students, as well as a postdoc here who had done all of these nice work, and finally many colleagues who have supported me through collaboration and discussion, and of course the funding agencies that have supported our fundamental work.